So let me just present you, Sophie, and then we can start. So welcome everybody to the third section of this seminar in Equivariant for this an application. Today we have the honor to have Sophie Kriz, that she's a so smart student of just in bachelor and has a lot some papers, a lot of papers published, also a book. Yeah, so we are really a pleasure to have you, and the time is yours.
Okay, thank you very much. Thank you very much for inviting me and also for coming to listen to my talk. I'm really happy to be speaking here today. Okay, so to begin with, today I'm going to be talking about new completion theorem and its application to giving a counterexample to the Evenness conjecture for homotopical Keyboardism. Okay, so I'm going to begin with some brief recollection of some definitions and sort of the non-equivariant side, which will offer some intuition for the equivariant side before talking about my specific completion theorem and results. Okay, so to begin with, let me recall the definition of the complex Keyboardism. So today I'm going to only be talking about cases of finite groups G, even though some generalizations also exist for compact Lie groups, but a lot of the sort of structures and results which I'm going to be using sort of break down in that case. So I'm only going to be treating the finite case. Okay, so recall that this complex Keyboardism omega Gn is given as the space of compact smooth n manifolds with some G action, such that there exists some n, such that if we look at tau m, tangent bundle, and we direct sum with, and where we consider this as the trivial fixed real bundle of dimension n, this has a G equivariant complex bundle structure. And then sort of what sort of characterizes this structure is this equivalence relation, where of course we have to stabilize n. But other than that, we have this sort of this Keyboardism relation, which says that if we have some, let's say, m0, then and some m1 sitting in this omega Gn as elements, then they're equivalent if there exists some manifold M with boundary such that if we look at the boundary of this M, it's equal to the disjoint union of M0 and M1. And we also have to choose some trivialization. So we have that this, if we look at the tau m and we restrict it to this boundary, then this, well, it looks like tau boundary of m plus this trivial one-dimensional real bundle, which basically, and what this does is it sort of, if we look at this sort of drawing, like let's say this is our M0 and this is our M1, and this is our M, then what it does is it just sort of chooses an orientation. So like one side goes out and one side goes in for these M0 and M1. Okay, so non-equivariantly, let me recall that in this case, we may construct sort of the classifying space BUN as a Grassmannian, so as a space of these n-dimensional complex vector subspaces of C infinity, where here, of course, we interpret this only as a infinite direct sum of some copies of C's. And this has a universal bundle gamma and C, which is just given by the fiber over a point in BUN. Well, point corresponds to an n-dimensional subspace, so it's just that space itself. And this sort of universal bundle is fairly useful because, for example, if we have some CW complex X, it gives us this isomorphism, this identification, this isomorphism between isomorphism classes of complex n bundles over X, with maps going from this X to this BUN. Just by, if you have some map F from X to BUN, we just consider its pullback of the universal bundle along F. And in this case, we can form this sort of pre-spectrum, which I call here D2n, where we just take each D2n to be the Thom space of BUN with this universal bundle gamma n. Which basically just means how this should be visualized is we take the union of this gamma nc with a point, and then we have to do something special with the topology where we take the co-limit of one-point compactifications of compact Ks, which sit in there. And okay, so this forms a pre-spectrum because, for example, if we consider the second suspension of such a D2n, this looks like sigma 2 BUN gamma nc by definition, which is BUN with now the Thom space with the bundle gamma nc plus this trivial, which maps naturally to BUN plus 1 with gamma n plus 1c, which is just our D2n plus 2. So this, we can see this forms a pre-spectrum. And then what the Thom spectrum is, this MUN, is we just spectrify it. So we take this, we do this operation where we take the co-limits of these loops, omega 2m minus n of the D2m. And this forms a spectrum, which is called MUN. So this is a non-equivariant Thom spectrum. And one special thing that it satisfies is this non-equivariant Thom's theorem, which says that if we consider on one side the nth non-equivariant complex Keyboardism, then this is actually the same as the nth homotopy group of this spectrum mu. In other words, its coefficients. And further, what these coefficients, if we look at them as a graded ring, so we consider that, so we look at pi star of mu. What we actually find we get is z with these sort of polynomials of variables, infinitely many, x1, x2, and so on, where each xi appears precisely in degree 2i. So we already have some, so there's like some sense here that we only are generated in even degrees. But here, of course, again, this is very important that we're working non-equivariantly. So the G that we've chosen here is a trivial group. Okay, so that's sort of a brief summary of the non-equivariant side. So now let me talk about the equivariant side and a little bit about these evenness conjectures. So equivariantly, so what we're now going to do is we're going to take BUNG to be the space of these n-dimensional complex vector subspaces of the complete universe, or the complete complex universe. And what that means is just we are taking a direct sum over infinitely many copies of the irreducible complex representations of G. And we can actually note that this is actually the same as if we were doing regular representations instead. Just because, like I said, we're talking about G finite. Okay, and so, and a similar story sort of follows with this, with how we define this sort of pre-spectrum and spectrify it to form this G equivariant Thom spectrum, this MUG. And one thing maybe that should be noted is it's now ROG graded. Instead of just being. So, and this just means that the grading ROG is this free abelian group on irreducible real representations of our group G. And so then what we do is, what we can find is that there is actually a map going from this G equivariant complex Keyboardism omega Gn to the coefficients of MUGn. So again, here by this I just mean, I'm just using this standard notation that MUGn is just what we get from applying MUGn to a point. And so yeah, so there is a map between these two spaces, but what actually we find is that it's not an isomorphism if G is non-trivial. For example, it fails surjectivity even in like very small cases of G, such as Z mod 2. Oh. And so we see that this first sort of part of the non-equivariant Thom's theorem doesn't carry over to this G equivariant side. But there could potentially be a question asked about whether sort of this evenness, this even generation maybe holds in this case, which sort of leads to these two questions called the evenness conjectures. So the first one is called the geometric evenness conjecture, and we need to phrase it twice again because these are not isomorphic. So there's one possible formulation for this side and one possible formulation for this side. And what we get, so what they say are the geometric conjecture states that this complex Keyboardism omega G star, and okay, and how I'm interpreting that is that this basically this forms a Z graded G equivariant homology theory. This omega G. By just, if you've got some X taking manifolds, the sort of space of manifolds with maps just to X. For G equivariant X. And so the conjecture states that this is a free mu star module generated in even degrees. And you can also phrase a homotopical version of this evenness conjecture for MUG star, which is states that this is a free mu star module generated in even degrees. Okay, so let me first mention the history of these two conjectures. So these date back to the 1980s. As they're sort of first formulated by Rowlett and later reformulated by Comezaña. And there's sort of been a continual interest in them and sort of what can be proved. And for example, the geometric version was recently mentioned in Bernardo Uribe's 2018 ICM talk, and it was also spoken about in the last talk, where Bernardo Uribe announced the fact that this first geometric version actually is false. And he produced these counterexamples with joint work with Eric Samperton, Carlos Segovia, and Andres Angel. And so, yeah, so there's been a lot of there's been a lot of study of this geometric evenness conjecture, and and it was disproved by these counterexamples. And today I'm going to be talking about this, however, this homotopical evenness conjecture for this MUG star instead of the complex Keyboardism. And I'm actually also going to produce a counterexample to it. Okay, so and I'll talk a little bit about how this homotopical evenness conjecture relates to this geometric evenness conjecture. So first of all, let me talk about a little bit about sort of how these two conjectures are sort of mathematically related, if there's any sort of implication between them. And let me also introduce a slight rephrasing of this homotopical evenness conjecture, which I'll call the flat homotopical evenness conjecture, where instead of free, we consider that the statement to be that MUG star is a flat MU star module generated in even degrees. So it's a slight weakening of the statement. Okay, so let's consider this. So like the ways of going between sort of the geometric and homotopical side. So for example, one way this was historically done was using this construction of Brucker and Hooke, which I'm going to call omega g big here. And what it does is we look at this direct sum over n of omega g n in degree n times 2 times g, the number of elements of g, minus 2, of S n R, where R is just this complex reduced regular representation of G. And as you can see, this is just the dimension, n times the dimension of R. Yes, and this should be reduced actually. Sorry about that. And again, just to justify why we can think about this reduced, I'm still again recalling, thinking of this as homology theory. And so what Brucker and Hooke proved was that there exists some orientation classes, EV, in this reduced omega g in dimension v of SV. Okay, this let me just make a short point. This denotes the 1-point compactification. Of this representation V. For any V faithful finite dimensional complex G representation, such that in particular, if we look at ER, which sits again in here, what we get is that if we invert it, so if we take ER inverse of omega G big, this is actually isomorphic to the coefficients MUG star and we just throw back in ER and ER inverse. And so in particular, what this would mean is that if we had a version of geometric evenness for this omega g big, then it would imply homotopical, this flat version of the homotopical evenness for this MUG star. But as you can sort of see that we've sort of, it's a lot more difficult to check this geometric evenness for omega g big than it is for just this original complex Keyboardism. So there really isn't quite such a implication between these two sides of the evenness conjecture. Okay, but let me also talk a little bit about the counterexamples, a specific aspect of the recently announced counterexamples to the geometric evenness conjecture, which were talked about by Bernardo Uribe last time. It's that this class, which he considered, what we saw was that these considered groups all had non-zero Bogomolov multiplier. Which has some interesting sort of algebraic consequences, because this Bogomolov multiplier, it's a really interesting algebraic invariant, which has some deep applications to certain other sort of like open algebraic conjectures. So I'm going to talk a little bit about that as well. And I guess let me introduce my counterexample here to the homotopical evenness conjecture. So I claim that it's false for the P-CLF subgroup, G sitting in GL4 of FP. So, for example, we can consider sort of the one as those elements look like these lower triangular matrices, like so. So as you can see, G is generated by such elements for A through F in FP. So we can see that the number of elements in G is P to the 6, which should be what we expect for GL4 FP. And it's true for all P prime greater than 2. So let me talk a little bit about sort of the Bogomolov multiplier and what the significance of that is from like an algebraic context. So let me first begin with the definition. The Bogomolov multiplier of a group G is given to just be the sort of set of all the subgroup of these C's sitting in this second cohomology of G with Q over Z, restricting to 0 on all abelian subgroups H sitting in G. And this has, like I mentioned, this has a deep algebraic application, for example, to something called the Netter problem, and which is stated as follows. Which basically, so what the Netter problem asks is, it asks for which groups G is it true that for G acting linearly and faithfully on some vector space with basis x1 through xn. And we look at sort of this G, the G representation, C, we look at the sort of fixed points of this G action on these rational functions in these variables x1 through xn. One could ask if this will be isomorphic to another field of functions, C of t1 up to tn, for some ti's, some rational functions of the xi's.
Just a small comment, the ends don't have to be the same on the two different sides.
Oh, I mean, I shouldn't they sort of just by like dimension?
Well, but the invariants could be much smaller dimension.
Okay, all right.
Yeah.
Yeah, okay. I think perhaps I guess it's not super relevant to where I'm going with it. Yeah,
Agreed.
it's like the question's like basically whether it's isomorphic to another field of rational functions. Yeah. Anyway, the TIs should be some sort of rational functions of the XIs. All right. And I guess here I've stated it for C over this field C, but it's sort of historically asked for Q. And for example, one like sort of interesting application of it is that if it's true, then we actually get generic solutions to the inverse Galois problem, which basically asks if there's some field extensions K of Q, such that the Galois group of this field extension is isomorphic to this chosen group G. And I guess this implication is by like Hilbert's irreducibility theorem, where we just plug in values to T. The T's. Yes. So basically, the reason why we're doing it over C is because if it fails for C, then it fails for Q as well, or for any number field. And it is known to be false in general. This isn't true for all G's, but it's still an open problem for which G's it might be, for which G's it is true or it is false. And that's still an open problem, but what it is known that if the Bogomolov multiplier of a group G is non-zero, then G forms a counterexample to the Netter conjecture. So for example, all of these have non-zero Bogomolov. All of these examples, these counterexamples to the geometric evenness conjecture have this non-zero Bogomolov multiplier. So they all also form counterexamples to the Netter conjecture. And okay, and let me also talk a little bit about my example and how that fits into it. What I actually found was that the G, it's a group of order pizza 6, and those are fairly well classified. And it was actually found through some computations by Chen and Ma that this G, this PCLF subgroup, has of GL4FP has Bogomolov multiplier 0. And actually, it seems that in that case, the Netter problem is unknown. And so one can ask sort of whether there is some sort of connection between the algebraic and topological sides. So whether there's some sort of connection between these conjectures. So for example, perhaps it might be true that if G satisfies the network conjecture, then G should also satisfy, for example, the flat homotopical evenness conjecture. Okay, so that's a little bit about this sort of algebraic application. And I think I'll spend the rest of this talk, the next 20 minutes, just talking a little bit about my proof. And it comes in a couple steps, or a few steps. So sort of the first step is constructing an orientation class. And I'm going to use this to form a completion theorem. And then I'm going to argue why that applies and how it helps to this specific case, this specific subgroup, which I'm looking at. Okay, so to begin with, I'm going to look at constructing an orientation class. And what my result here says is that if I've got some finite dimensional orientable faithful G representation V for some finite group G again, then first of all, if I denote the dimension of V by n, then if I look at this nth homology HNG of this 1-point compactification SV with this excuse me, with this constant Mackey functor Z, where just recall this is given by, if you've got some orbit G over H, just putting this to be Z and having the restrictions to just be the identity. Then I claim that this gives us Z, actually. This is isomorphic to Z. And sort of a more general, like kind of a more general state version of this is that if I've got some general Mackey functor M now, and I look at for any sort of degree, which I can choose M greater than 1, then if I look at this reduced homology in degree M times the dimension of V of the 1-point of the MV with coefficients in M, then I claim that this is exactly what we exactly get is M of G over E. So this is sort of a more general version of the first. And what's actually kind of interesting is that similar statements also appear in the Hill-Hopkins-Ravenel paper on the non-existence of elements of Kerr-Variant variant 1. Even though I didn't know it when I was doing this theorem, that's actually kind of interesting that like sort of similar results are used. And I guess to say a couple words, yes?
What is little m in this theorem?
Oh, little m, we're just choosing, this is true for any little m greater than 1, if you're talking about this.
Oh,
this
I
part.
see. You're multiplying the representation by m. I see. Okay, thank you.
But yes, that's right. Yeah, and I guess to say a couple words about the proof, basically, I'm going to use, I sort of use this fairly heavily, this sort of faithfulness, as in like if I've got some non-trivial subgroup H sitting in G, then because we're faithful, if we look at VH, these fixed points, this has to be in but not equal to V. So in particular, the dimension has to be strictly smaller. And what that means is that there's no top cell of this SV in VH. And what that means is that the top cells are free. And that's sort of the key point in proving this, both of these sort of versions. And okay, and so just to consider sort of like what this means, like I guess considering one sort of important example, I guess, is when we like apply it to the Burnside functor. So the Burnside Mackey functor. So what I mean by that is if I look at on this side, this reduced HGK times the dimension of V of SKV with the Burnside Machifunctor. This turns out to be isomorphic to A of G E, this sort of trivial orbit. And this, in the case of the Burnside Machifunctor, this is actually exactly Z. And so basically what we do is to find the orientation. In this case, what we do is we look at the EV, which gets sent to 1 in this C. So this is sort of, yeah, so that's sort of like an example of how we're going to find orientation using these isomorphisms. Okay. And in particular, so that's enough for the first step. And sort of the next step of my sort of proof of this broader statement is going to be that inverting this orientation gives Borel cohomology, actually. So what I mean by this is if I've got some Machi module M now over some Green functor R, which is just some sort of ring, some sort of version of Machi functor, which corresponds to like some sort of ring structure. Then there exists some orientable faithful G equivariant representation V, such that if I invert this EV inverse HM, this is equivalent to F of EG plus to HM of G over E. And maybe some quick points about what I mean by this. So first of all, this is just disjoint base point, this plus. And here, I guess I am considering this stuff as a naive G spectrum, meaning that there's a non-equivariant G action. And on this side, I guess, just to write it out, I'm considering here the homotopical limit of these maps, where I go from HM to this sigma M times the dimension of V minus MV of HM via this orientation, this EV. And I keep going like this. So for example, the next step, I'm going to be at sigma 2 times this MV minus MV, and so on.
Excuse me, what do you mean by non-equivariant G action? What does that mean?
Oh, sorry, maybe that's confusing. Maybe it's just best to say that I just mean kind of that there's this, that we've got this sort of naive G spectrum. So we're not really working in like sort of this most sort of strict context, which
So
we've
does
been
that
looking
mean
at.
it's an ordinary spectrum in which every space happens to have a G action?
Yeah.
Okay.
For example, yes. So anyway, just like, I guess, just to say a couple words about this, what I mean by this is I look at this homotopical limit of, and I start with HM. So all the top cells here are free. And at each step, just what I'm seeing is sort of the range of free cells expands. And actually, I don't think that's quite what I mean by a naive G spectrum here. I don't mean there's like a non-equivariant G action is wrong. I just sort of mean that it doesn't like desuspend under the representation, only under the fixed spheres, really. That's kind of what I mean by this here. But again, so the main point of the proof is that as I keep applying this orientation class, the range of the free cells keeps expanding. Okay. And so now let me get to my completion theorem, which says the following. So let me first state this sort of key condition, which will be necessary to the statement. And that says that given some E, if I've got some G spectrum L, what I consider, we consider this as condition star, such that, which says that there exists some finite R, such that for every G space X, the equivariant L Atiyah-Hirzebruch spectral sequence converging to this L star X collapses to its rth page, this ER. This is, of course, comes from the Whitehead filtration. Okay, and let me state the actual theorem now. So basically what I do is I suppose that I've got suppose that there exists some orientation class, EV twiddle in this in this sort of reduced E twiddle in degree dimension of V of this 1-point compactification SV. Or in other words, this is just E dimension of V minus V of the point, such that if I consider what I get from taking this composition, new smash this SV minus V composed with E smash this orientation going from E to E smash SV minus V. And I guess this new just denotes the operation of E. So we assume that it says some ring spectrum. So basically, I need to suppose that this forms an equivalence. And then what my claim is that if L is E satisfies this assumption star, then there exists some decreasing filtration Fi on these pi G star of E, such that, first of all, if I look at the limit of this pi G star of E over pi G star Fi of E, then as I goes to infinity, then this is isomorphic to pi G star of F from EG plus to E. And secondly, well, F0 of pi G star E should just be pi G star E itself, and F1 should give the augmentation ideal. And finally, F actually does truly form a filtration of rings. And let me also state a minor, a little bit of a generalization of this. So if I have some K, which is a module over a module spectrum over E, then what I claim is that it's enough to just have this assumption for L equals to K. And then not necessarily for E, that's sort of a key point. And then what I get is that I can replace all these E's also with K. So there's now Fi is a filtration on pi G star of K. And I still have this same isomorphism here. And this fact about the F0 of pi G star of E, pi G star of K. And I'm not sure if this augmentation ideal part of it still carries through to the module setting. Yeah. But yes, but it should now be filtration of modules rather than rings. So this is sort of like a generalization which I'm going to be using to actually get the counterexample from this result. And let me talk a little bit about the proof. So first of all, what I do is I consider like the homotopy filtration from this homotopy decreasing filtration tau greater than or equal to n+1 E and to tau greater than or equal to NE. and to n-1, and so on. And this sort of clearly has homotopy limit 0, because if I were to take cofibers of canonical maps into this E, that would give us this sequence from, well, for reversing all of these inequalities. So tau less than n plus, strictly less than n+1 E to tau less than n E, and so on. And that has homotopy limit E. So this has homotopy limit zero. And what I keep doing is I keep applying this orientation. And recall that yes. I keep applying this EV twiddle. And that should send this tau greater than or equal to n+1 E to tau greater than or equal to n+1 E, smash this SV minus dimension, and so on for n and n-1 and so on. And I just can keep repeating this. So keep applying this EV. And what that keeps doing is it keeps smashing with another copy of this. So for example, at the next stage, I get everything smashed 2V minus 2V, and so on. And all of these are going to have homotopy limit 0, because we have each of these have, because we're applying this sort of equivalence, which we assumed, this E is equivalent to E smash S, any number of copies of this SV minus V. And what I'm going to do is then I'm going to take this J decreasing filtration, this JFI, to be tau less than IE smash S J times V minus V. So for example, this one is just going to be 0. So we've gotten this sort of sequence of these filtrations. And I'm going to consider also this. So we obtain this, where I'm going to, so each of these have whole limits E. We're taking the whole limit in I now. And I'm going to call the spectral sequence in homotopy groups, which comes from this, EJ. Okay. And then, so now here's where we're using this key assumption star. And what it means is that we're going to get that each of these JEs will collapse to some rth page ER for some finite R less than infinity. But sort of the key point here is that it has to be the same for all of the J's. We have one R, and this is where we're using this assumption star. And so basically now we take sort of this colimit and we form this infinity E and infinity F just by keep applying this EV twiddle. And this gives us that this has to collapse to its rth page as well. And then from there, it's just some formal sort of results, sort of the main part of which is proving that this, if we look at the ith part of this filtration, so this infinity f is going to be the filtration which appears in the theorem. So it comes down to sort of, for example, proving that the ith part we get is a homotopical limit in J from this tau less than I of E smash S J V minus V, and this equivalence to FD plus 2, yes, to tau less than I E. Yeah, and that pretty much gives us sort of this if I can find the slide, and that gives us this part which we want. And so that's sort of like the key part of the theorem. And I guess very quickly, I'm going to say how I get the counterexample from this. Basically what I do is I suppose that this MUG star, I'm going to go by contradiction. So I'm going to suppose it does form a flat MU star module in even degrees. And then this ring spectrum MUG has a module spectrum Kn over Mu with MUG. This just here is more of a K theory. And by flatness, which we assume is this, if we take these coefficients of this module spectrum, we just get this Kn star tensor Mu star with MUG star. And our assumption says that this has to be concentrated in even degrees. But on the other hand, it actually, the key point is that this module actually turns out to satisfy this assumption star. And what that means is that we can apply this completion theorem and get that there exists a suitable completion of these coefficients, which is isomorphic to this Kn star Mu. And so this too has to be concentrated in even degrees from our assumption. But this actually contradicts some direct computational results of Kriz and Lee coming from, for example, 1997 and 2000 in the case when n is 2. Because, for example, we've got, I think P equals 3 was in 1997, and all primes greater than 2 were in 2000. So they constructed some odd elements. So this cannot be true, which sort of concludes my proof of this counterexample. And also that looks like all I have time for. So thank you very much for listening.
Thank you very much, Sophie, for this talk. So we start with the questions. Just unmute yourself.
Yeah, so these, sorry, the examples are PSL4FP. Is that right?
Let me see. Yeah, they should just be these. They should just, again, I mean, they should be exactly.
Yeah, GL4FP. Okay.
Yeah, it's exactly the PCLF subgroup of this, generated by things that look like this.
Right.
Or exactly the things that look like this.
But those groups specifically came up in these calculations, so Kriz and Lee.
Yes, that's right. Yeah, that's right. That's sort of precise. Yeah, this is precisely. That's exactly right. We're using this.
Okay.
This is sort of like, yeah.
I guess I have another question. So in our case, in the geometric case, our counterexamples were all P groups at first. And what we have learned, I guess we haven't written this down anywhere, but for simple groups, their Bogomolov multiplier, well, this is known. The Bogomolov multiplier of a simple group always vanishes. So simple groups, the geometric Evenness conjecture might very well be true for simple groups. What we know is it can't be false because of two-dimensional reasons. So I don't know. I guess I'm wondering if you have any thoughts about like either simple groups or perfect groups in the homotopical case.
I have to say, that's very interesting. I mean, I'm not sure. Like, again, there sort of seems to be some sort of connection between like this things which happen on the algebraic side and like this topological stuff, like this homotopical evenness conjecture, for example. But I have to say, I mean, here it's sort of like the significance of the group is precisely because there's like this specific calculation in this case. And honestly, I'm not sure if it's sort of what sort of like the generalization for like a general group should sort of what results should sort of really be true there. But it does seem sort of really interesting. Yeah, I'm just noticing that there should be like a completion here. Sorry. Just for this
so maybe just something to note. There are quasi-simple groups. So these are central extensions of simple groups that do not have vanishing Bogomolov multiplier. So there's just a couple of them, and so those are the only examples I know of, for example, perfect groups where the Bogomolov does not vanish. So yeah, I maybe just something to point out. That's all.
That's interesting. That could be like some, yes, that's very interesting with like what the connection could be, if there's anything.
Yeah, I mean, maybe for just to throw a question out there for everyone to maybe chew on is in either the geometric or the homotopical version, do the conjectures hold for simple groups or things that are not far from simple groups? So.
Another question? So could you mention just a simple reason why for the prime p equal to this is not a counterexample?
Sorry, could you repeat that? Oh, it's for p equals 2. Right. I guess it's just because like this these computation, I'm not sure if like it actually is a counter. It's just because like these this sort of computational result was only sort of for these primes greater than 2. So yeah, that's just sort of the reason why I have it in my statement.
And your counterexample, in which degree lives? In the geometric part lives in dimension 2, but here the counterexample in which degree lives?
Oh, I guess. Okay. So I guess in my actual sort of proof, it's sort of not super used. It's kind of more of a black box. I guess I could probably talk more about it. It sort of gets kind of technical and into these sort of actual computations by Kriz and Lee, which isn't quite my work. But I'd be happy to talk about it more over email or something like that. It's yeah.
Maybe just to clarify, Kriz and Lee are breaking some kind of evenness. Is that correct?
Yes, that's right.
So,
they're finding an actual element in odd degree.
Is it torsion? Because that's what we broke.
That's right. I mean, I think here the thing that breaks more is like the evenness rather than like the freeness part of it. Because I remember from the last talk that you guys talked a lot about, you found these torsion elements that really broke this freeness of the statement of the conjecture.
Right.
Here, I feel like the actual like the part which breaks is more closer to like just the even degrees in this case.
That's interesting. That's very interesting. Yeah.
It would be interesting, yeah. Because here,
we basically don't know about odd degrees. We were going to look at degree 3 next. We haven't done it yet, but yeah. Oh, sorry, I think I interrupted you, maybe. Yeah,
no.
Yeah.
Sure. Let's see. I keep coming back to this. I think like we need something like this rather. Sorry about this. This should be K and star BG. Yeah. Because, right, how does it depend on the G? Sorry about that.
Sure.
Is there another question? So, just thanks to Sophie for this wonderful talk.
Thank you, Sophie. Great talk.
Thank you very much for letting me speak.
No, I will stop